Welcome to the world of bioreactors. This step in the biopharmaceutical process is all about scaling up. The cells are now ready to keep growing, but they need to do so under tightly controlled conditions, and bioreactors let us do just that. So, what is a bioreactor? A bioreactor is a large vessel or tank in which cells grow and manufacture product. They can range all the way from 50 liters to 50,000 liters, and they offer control of biological activity through the manipulation of one or more environmental variables. We call these variables critical process parameters, or CPPs. There are two main types of bioreactors used today: stainless steel bioreactors and single-use disposable bioreactors. Stainless steel bioreactors are the most popular and have traditionally been the old favorite in the biopharma world. They are well understood and have been around for decades. Stainless steel bioreactors are usually available in very large capacities and provide advanced methods of measurement and control. Single-use or disposable bioreactors, on the other hand, are reactors equipped with a disposable bag usually made of plastic. They are much smaller in capacity than stainless steel bioreactors and have recently become very popular since they are easy to set up, deploy, and require minimal cleaning and maintenance. Both systems have advantages and disadvantages. So today, companies are implementing somewhat of a hybrid approach. For instance, a room filled with both stainless steel and single-use bioreactors. So what happens inside a bioreactor? First, we must know that all cells require nutrition to keep growing and manufacturing product. These nutrients can be found in the media inside the bioreactor. As you can see in the diagram, bioreactors are equipped with an agitation system that allows the cells to be evenly mixed throughout the media. This agitator suspends the cells and provides the oxygen necessary for cell growth. Bioreactors are essential to creating the conditions to optimize the growth of these cells. For this process to be an effective and efficient one, we must rigorously monitor and control the environment within the bioreactor. Critical process parameters, or CPPs, can be tightly controlled. Examples of key CPPs we might want to monitor and control include temperature, pressure, pH, oxygen, nutrient levels, agitator RPMs, airflow rate, and cell count. As we briefly mentioned, mixing inside a bioreactor, cells grow and manufacture a product. The self-growth pattern is comprised of 4 stages: lag, log or exponential, stationary or plateau, and death. When a cell is first introduced into new media, it must adapt to its new environment. Thus, cell growth does not start immediately. This is known as the lag phase. Once the cell has adapted to its new environment, the self-growth takes off. These cells now enter the rapid growth phase, which we call the log or exponential phase. The cells will double, they'll double again, and so on. As the nutrients in the media are consumed by the cells, toxic metabolic waste products will build up, cells begin to die, and the growth rate will eventually slow. When just as many cells are dying as are dividing, we enter the stationary or plateau phase. At this point, the key nutrients in the media are completely consumed, and the fermentation process is stopped. If the process could continue, then we would enter the death phase, in which more cells die than divide, and therefore the overall cell count would decrease sharply. After the fermentation process is completed, the media may be transferred to a broth tank and will later enter the separation and capture step, which we will discuss in the next section of this module. Let's take a look at the 3 main production strategies: batch, fed batch, and perfusion or continuous strategy. In a batch process, nutrients are added at the beginning. The cells go through the lag, exponential, and stationary phases and are then harvested one time at the end of the cycle. It is important to note here that the volume inside the bioreactor stays constant throughout. Essentially, once nutrients are added, we let the process play out and then retrieve the product at the end. No further intervention. In the fed batch process, we intermittently feed nutrients into the bioreactor. Therefore, the volume inside the bioreactor will not be constant the entire time. The culture will go through the lag and exponential phases. Then we will feed it nutrients, the cells will keep growing and producing product, and then we will reach the stationary or plateau phase. In the end of the process, we retrieve the product. Finally, in a perfusion or continuous type of process, we are simultaneously feeding nutrients to and retrieving product from the bioreactor. The stirred tank mixing method that we discussed earlier falls under this production strategy. Guidelines. There are some important regulations pertaining to bioreactors and the fermentation process in general. The ICH, which stands for International Council for Harmonization of Technical Requirements for Pharmaceuticals for Human Use, has guidelines that ensure bioprocesses happen safely and effectively. Some of these include that equipment used in manufacture of APIs or active protein ingredients should be of appropriate design and size. Reactors should be appropriately identified. Substances associated with operation of equipment, such as lubricants, coolants, etc., should not contact intermediaries or APIs. Closed or contained equipment should be used whenever appropriate. Furthermore, where addition of media is needed, closed or contained systems should be used when possible. There should be appropriate procedures in place to detect contamination and determine appropriate course of action. Records of these contamination events should be maintained. Critical operating parameters, such as pH, temperature, or agitation rates, should be monitored to ensure consistency with the established process. Productivity should also be monitored. And finally, fermentation equipment should be cleaned, sanitized, and sterilized.